using start sharing. I think it's only allowing me either to share the screen or the webcam, is it?
To be honest, I'm not sure.
It should,
Now,
Yeah, wait.
now,
I will stop the screen share. And yeah, I think it seems to allow either.
okay.
What's happening here?
I think we are we online yet?
Yeah,
Okay.
so everything's ready.
I think I'm not able to switch on my video now. Only the okay, no, now it came back. Yeah, okay, good.
Okay, perfect.
perfect.
Okay. Okay, so welcome everybody. Welcome to this tutorial of LADC 2021, Latin American Symposium on Dependable Computing. It is my pleasure to welcome Dr. Amitabh Trehan. Amitabh is an associate professor at Durham University in UK. His broad research interests are in computer science theory and algorithms, especially those arising from or applicable to real-world and human-engineered systems. Amitabh has specific interest in distributed algorithms, complexity, networks, graph theory, and game theory. And current work includes designing efficient distributed algorithms for robustness, self-healing, and self-start properties in systems under attack from a computationally unbound adversary, questions about algorithms in distributed and biological systems, and game theoretic and other mechanisms for evolving and dynamic networks, such as peer-to-peer and social networks. He is a fellow of the UK Higher Education Academy and fulfills various teaching and administration roles, including coordinator for undergraduate final projects. And today he will present us with a tutorial on self-healing distributed algorithms. So again, welcome Amitabh, and it is a pleasure to have you here.
Thank you very much, Leonardo. It's my pleasure to be here at the tutorial. It's would have been nice to be in Brazil, but it's similar weather here, I think, around 4 degrees.
I'm not sure.
Temperature-wise, but yeah.
Very unlikely, very unlikely.
Very unlikely. That's why I'm jealous. So yeah, thank you again for the introduction. It's slightly outdated, that introduction, though. So I'm at Durham University. I'm not the projects coordinator anymore. I'm actually heading a new research group called Network Engineering Science and Theory in Durham. So it's a very exciting time here at Durham University because we are growing, and the computer science department is growing very fast, in fact. And we have now gone to about 50 members from about 20 members 4 years ago. And in fact, we are hiring in my group. We have an assistant professor position open in distributed computing and network. I mean, all aspects of network and computing algorithms. So if there are any young people, smart people there who are interested.
Very interesting. Yeah, there will be for sure.
Plus, in fact, we are also hiring at a full professor across the department, and other openings also. There are like 4 or 5 openings coming up. So yeah, so it's nice times. So I'll move on with the tutorial. So let me see. Okay, which buttons to press where? Yes. Okay, so I'm going to talk about like it says here, self-healing distributed algorithms. And please feel free to interrupt or ask questions. And I can in fact also see the chat, I think, in the system. So if you want to type in the chat, I think that may work also, and I could stop and ask. All right, so this is quite a catchy term. So maybe first we'll think of healing. So now I found this on the internet, and of course, I think when you start looking for healing, most likely you're going to find all of the yoga poses and all of the nice meditation things. Unfortunately, we are not dealing with such strong kind of healing. So we are dealing with healing in a different way on networks or computers. So let's think of what I can call as a healing game. So what you have here, you have an attacker and a healer. And here what we are trying to heal is actually, in some sense, a graph. So you have this graph, and the attacker is attacking the graph, and the healer is trying to heal the graph, right? So I don't know if I can use any drawing tools on this. I doubt it actually. So maybe we'll go without the.
You should have a pointer, kind of laser pointer.
I should have a laser pointer.
Yeah.
But
not drawing.
Okay, yeah, laser pointer may. Are you able to see my mouse when I run it here? No.
No.
Okay, not a big issue. Yeah, I don't see the pointer exactly, but okay, not a problem. Okay, so I mean we'll come to that again. So, but at least it gives us some idea. So I want us to think about this sort of healing game. Now, what's happening in this healing game? You have the attacker and you have the healer, right? So the attacker is going to do something which is basically attack, that is by removing this node. So it has attacked this node, and what this has done is basically taken this node out of action, removed it, crash failure, whatever you want. Those who are familiar with distributed concepts, you can think of this as a crash failure. That is, the node has completely gone. Now, the game is like this. The attacker is picking a node to remove, and the healer has to add back some edges. So what do you think would be nice edges to add in this system? So of course, I don't have any labels, unfortunately. So you may have to just say from where to where or something like that. So let's say we have a node on the left. Are you able to see my mouse or the point? No, not the pointer, right? Or can you see the pointer?
The mouse, yes. Mm-hmm.
Oh, you can see the mouse. Okay, good. So we have a node here. So you can see all of these nodes are potentially here nearby. So what do you suggest? Which edges should be added back? So the game is the attacker can remove a node, but the healer can add new edges. So what do you think would be the interesting or the important edges to add back? Anybody? Just sort of
maybe the 3 edges that make the graph connected again.
Right. So yeah, absolutely. So the first important point is somehow we need some edges which will keep the graph connected, right? So I mean, so we may want to choose, say, now here you have 3 components, right? 3 different components. So you may want to choose 3 edges which will make it connected. So not just any 3 edges. So we'll need 1 edge from each component, maybe from this to this, from this to this, and from maybe from this to this, right? So maybe we'll take 3 edges and we at least get connectivity back, right? We can go on. So, okay, just now here, okay, I've got connectivity back, but am I giving something in return? Is it possible that I may actually be trying to target some other node? I'm trying to target some point in the network where I want something to overload, right? So for example, we can think if you think of this graph as a network, we can always think of the number of edges you have as your load into the system, and the topology or the paths you have as sort of representing the distances or paths you have, connections you have in the network, right? So maybe the attacker also needs to think about a strategy, right? So maybe one strategy the attacker could think is, I am going to attack neighbors, right? So if I was to draw these new edges, maybe I will put one edge here, put one edge here to V, and put another edge to this third component. Now, the interesting thing is the attacker could be thinking, I want to target V. So it's not targeting V by deleting V, but by attacking V's neighbors. So it picks up another of V's neighbor, this red one, and removes it, right? Now, what edges do we need to add back here? In fact, do we even need to add back any edge? So what do you guys think? So do you think we should try to add back any edge, or you think we'll be quite happy with not adding back any edges? So this is sort of the game here. So, I mean, to cut sort of the suspense short, okay, I mean, we can look at this. Of course, remember we added 3 edges previously, so we are still in a connected graph. Now, if this node goes, actually we are not breaking up connectivity, right? So we're probably fine. We probably don't even need to add any edges. But the problem is, if you're not careful, what may be happening? Look at this path, right? 1, 2, 3, 4, 5, 6, right? Now, previously V was connected to, say, this node in the bottom by just a path of length 2. Now it takes it about 1, 2, 3, 4, 4 edges to reach V, right? So we are in fact, taking some risk. We may be actually increasing paths, though we have the option of putting in new edges and then making the path shorter. We decided not to, but that means we are actually now increasing the paths between 2 edges, for example, right? So on. Then this guy picks another neighbor V, and then it sort of removes this. Now again we have some issue. Should we add back an edge or not? Well, again, if we are really concerned about connectivity, we know we have to, right? Because we've isolated this node, right? So you're getting the idea now. So there are some things we really need to have. There are other things we need to think about, and that depends on you as the healer. What are your priorities, right? So if you're Harry Potter here, if you're the healer, and this is the bad guy is taking down things, and you as Harry Potter has to decide what edges do I put back, what I don't put back, what I don't. And here I'm not even talking about the cost of putting back edges right now, things like that. I'm just thinking of this as a game, right? So that's sort of the idea. So let's call this sort of the healing game, and we will visit it at some point, but I hope this gives you a bit of an intuition, right? Like I said, please feel free to ask any questions. I know those on YouTube may not be able to ask, but at least others can, right? Okay.
They are able also. There is, people will monitor the chat and will forward to us. So
I see. Okay, good. So good for them to put in something in the chat, right? So okay, that's just a very intuitive sort of introduction, just to give us an idea of maybe some simple game I want to play. So what the game I'm going to do later, remember it has a self in front. That's a self-healing game, calling this the healing game. And I'm actually, I think this game itself, I'm not sure if graph theory people study it, but I think they may. And I think there may be something interesting there in a normal setting. Our setting is going to be slightly different. Anyway, so what our setting is about networks, right? And so what we are going to move to the world of networks and think of this now graph which we had before, which could purely be thought as graph theoretic idea in terms of networks. So now networks, as we know, are everywhere. There are transport networks, there are natural networks in nature, there's networks in biology, there are networks in ecology, society, chemistry. I mean, just think of it, think of a subject, nowadays you have networks, right? But basically, what is a network representing? So it's in some sense talking about the field of combinatorics. So it's saying any if any objects have some relation to each other, you can almost think of them in terms of networks and connect them up. So what we are doing has probably some interest or application to that. Another motivation was that the power of the internet. So the internet is now, it was already 97% in 2007 for handling global communications, probably grown even more. So basically, we are in the age of networks now, and anything we can talk about in networks, and in this case about dependable networks, right? So self-healing is basically a fault tolerance dependability concept. So it's sort of important in that context. So now I'll step back a little bit to sort of take us towards understanding this a little bit deeper. So the question is, when we talk about computing, or when we talk about computers, about algorithms, what do we talk about? So generally, or the popular method is when we talk about centralized computing, right? So centralized computing is when you have the input given to a single machine, and you give it the whole problem instance and all the data, you have everything just to that single machine, and then it sort of finds the solution. So in this case, even though you have a network, let's say, this network may itself be given as an input to a single computer, and with the whole network to it. And then the question the computer may want to ask is, for example, what we are really interested in is we want to give one of the computers in the network a printer. So if it's a centralized setting, all the input is there. The centralized computer will simply decide, okay, I'm going to give the computer to this one, right? So okay, that's sort of the way you solve a centralized problem, right? Now, okay. So sorry, the heading should be different on the top. So now we move to the word of distributed systems or distributed computing. Now here the network is not given as an input. The network is itself the infrastructure. The network itself is the computing unit, right? So now here each of the nodes are actually computers themselves, nodes themselves. So now if you want to answer the same question here, the question now changes, because the entities which are actually computing are themselves participants, right? It's like our human society, right? We have to decide something, but it's influencing us also. The decision is influencing us also. So all of these things become much more complicated now, right? So if somebody has to win the Nobel Prize, and the person is themselves in the Nobel Prize committee, it may actually be quite tricky. So would they award themselves a prize, right? Kind of thing. So here there's a cooperation. Everybody has to think about something. So in that sense, distributed computing, distributed system is going to be where you have all of these multiple processors, multiple computers, but they only know a little bit. So they only have a local view. They don't have the whole input to them. And now the question they will decide now changes. So now instead of saying which one of them will get the printer, it's like which one of us will get the printer, because each of these computing units is now participating, right? So one way to solve this, for example, would be to have a token. So you have a token, and everyone when there's only one person who can have a token at a time, and whichever node has the computer at that time gets the printer, right? This is also, this person with the token is also known as a leader. And this was actually the foundation of the field of distributed algorithms, distributed computing, this problem of leader election in actually token ring networks. So in 1977, this was actually proposed as a problem and solved by Lee Lan, and this sort of started the field of distributed computing, distributed networks, with the problem of leader election. So finding one guy who's separate from everybody else. So this is of course massively useful in every kind of practical applications of networks and things, and peer-to-peer networks and ad hoc sensor networks. Very important problem to solve. Essentially a symmetry breaking problem where you distinguish a particular node. Now, for example, we had an algorithm in JCM15 which was the best algorithm for bonding both the time and messages. You can see this simulation from one of my students where it sort of says, let's see if I can play it again. So here you see all of the nodes are basically different colors, and then they start competing with each other, and they have different tokens, and the bigger token starts overriding the other tokens, and then it starts taking over. Now, as you can see, this node has already taken over the graph, but it doesn't network, but it doesn't actually know at the moment that it has won. So it still has to keep doing some more stuff. Still, it's like confident that, okay, now I have actually won over the whole place, which means I am now the leader. So that kind of thing is done, generally in distributed algorithms, distributed computing. Now this takes us to if you look at this, there's a few different things happening. So you began with a static graph, which is just a centralized algorithm where the input was static. Now you could change this a little bit. You could go to an in-between scenario where the input is actually now changing. So it's still centralized. You still have a single computer. It's solving the problem. But now the input is changing. So these are known as temporal graphs or dynamic graphs. Or if you've probably heard of dynamic algorithms, this is where your input is changing and you keep finding a solution. And then you go to the other extreme where you have distributed algorithms where the processing itself is done on a network, right? I mean, there's other variants. I'm just saying network. You can have shared memory, which is where you are actually have many processors, but they're sharing a memory. In the complete extreme case, the computers are not sharing anything with each other. They're just sending them messages, which is what we'll sort of live in. But here also you can have the flavor of it being static, like nothing changes, or dynamic, like things are actually changing while processing is happening. And of course, that's the extreme real world network is where everything is changing. But moreover, you can even have faults, right? Which is sort of our topic today. But before going further, one can now, I've already given you the clues on this, but one can sort of easily see that if you have a network, the most natural way to model a network is just by a graph. So you have this network, and now you represent it by a graph. On the graph, the graph itself is the network, and the vertices are the nodes themselves, and the edges are their connections. So if they can talk to each other, you make a connection between two vertices, right? And now what you can have is what we call as the message passing model. So you come to a formal model, which we call as the message passing. And here, again, we are trying to abstract reality. So we have to throw away many things. So we try to simplify things to get sort of understandable results. So this is sort of a very popular model in which we've made many assumptions, but important ones. So again, the graph is the model of the network. And this is the message passing model, which basically means the nodes are communicating only by sending messages to each other. Moreover, what we're going to assume in most of the work, I'll tell you where the exceptions are, is that they're going to be exceptions, but I'll let you know. So the simplest way to understand is what we call as synchronous and reliable message passing. So here communication is happening in synchronous rounds. So you can think that there's a global clock, and the clock is ticking. So every time the clock ticks, this process happens. That is, you have every node does what is known as processing, sending, and receiving. So what is that? The node decides a node creates some messages, and it puts them in its out buffer, and the message is sent, and it's received at wherever it wants to send on an edge. So it can only send a message to its direct neighbor, and when it sends the message, it reaches that neighbor before the end of this round, right? The next round, all the nodes in the system, they all pick up the messages from their in buffers, and that means they all receive the message from all their neighbors, and they can send to every neighbor, and then they process that message, they decide on new messages, send it out, it's received by the end of that round. So this basically puts a synchronous thing that everybody can do. Everybody does things together, which actually makes it much more, let's say, easier to handle than the other option, which is called asynchronous. That is, there is no bound on the delivery time of a message, right? Any question here? So this sort of basics I'm going through. Now we can move to another crazy thing, which is actually where distributed network algorithms have bit more power, is when your environment is faulty. And since this is a workshop about dependable computing, you're familiar with this. So now, in fact, what we're going to do is we're going to still do computing algorithms, whatever, but the environment is now faulty. You may have faults happening. You may have dynamicity, like I said, things changing in the environment. And this is when you devise fault tolerant or dynamic algorithms. The environment is faulty. You can see, for example, Voldemort may come. You can see the ginger-haired Voldemort, right, is breaking an edge, or somebody else creates a problem. Like if you're a fan of Pink Panther, even though it doesn't want to, Inspector Clouseau always ends up messing up things. So those things can happen. You can see there are multiple tokens here. There should have been just one token. How are we going to handle all of these situations? Because in real life, these can happen, right? So then the question becomes, which one of us will get the printer? Remember, because it's still distributed, despite failures or changes. So you may still have failures, you may have changes, but we still want to give a printer to only one at a time. So for example, now you can use what I call as self-healing, which we'll come to in a while. But a very important thing to get here is this picture, which I sort of designed at some point when I was thinking about this thing. Is if you are in the world of distributed computing, some things are crazy. And the thing which is really crazy is the models. So because reality is so complex, so if you're really trying to look at a network and trying to model how it's working, you have so many different parameters that it's mind-boggling to keep track, right? So we end up necessarily making many assumptions and then working in a space in which we understand we can give results, right? So for example, you can think in terms of architecture, timing, identity, knowledge, local memory, bandwidth, failure, behavior, right? And you can now come up with a combination of all of these architecture, which may correspond to the system you are looking for, right? The system you're designing a solution for, right? For example, the architecture could be your regular message passing point-to-point network. It could actually be a sensor network, wireless network, cloud overlay, shared memory, anything is possible as thing. And timing, like I already mentioned. Now, identity, I sort of assumed when I gave you the leader election example, I sort of hand waved that this guy overtakes this guy. But how do they overtake? So usually it's by an IP address, identity, whatever. They have some value with them. What if they don't have any value? What if they are all identical, have the same, exactly the same, exactly the same view, nothing, no difference? Then actually it is known you can't even solve leader election. You can't even distinguish nodes. So it can become crazy. There is the question of knowledge. So what do the nodes know? So again, this is not something you're going to face in centralized computing because everybody knows everything. I mean, this one guy knows whatever is to be known. But here, what do the nodes really know? Do they know more? Do they know less? Do they know estimates of diameter, size of the network, etc.? How is their local memory? Is the local memory unlimited? Is it small? Can they store much in the memory? What is the bandwidth? This is very popular sort of a question to ask because there's a big distinction between two kinds. The local bandwidth, local, which we call as unlimited bandwidth, called local algorithms, or congest algorithms, which are actually the practical ones with only logarithmic bits you can send in one time, right? But there have been some fascinating connections now drawn between other fields of computing and especially local distributed algorithms. And then finally, as you said, failure. And this is where there's power in networks or distributed compared to a centralized one, because in a centralized system, failure basically means you can't do anything, the system is gone. But in distributed or network thing, you can handle many failures can come and you can still keep going, right? And behavior, do the nodes actually, would the you have an algorithm and you design an algorithm, would the nodes in the network, would they actually follow the algorithm, or would they decide we don't need to follow? Are they intelligent? Do they have their own game theoretic intelligence built in, or are they trying to deliberately spoil the network, as in Byzantine faults, which actually become quite important in the new world of Bitcoin and cryptocurrency? You actually have nodes who may want to game the system. So all of these things come in, and all of these are motivated by reality, right? So in that sense, what I'm going to talk about self-healing is a very narrow definition of a very narrow area in which I work, which actually I can't even claim how realistic it is. So if you Google or if you try to find self-healing, you'll probably find this 100 probably different definitions and ways, and probably computer systems people look at it different ways. So mine is a very particular model I'm looking at, and of course I'm interested to know about the whole broad meaning of that. So I'll be disappointing in that sense not to be talking about the whole breadth of self-healing or meaning of self-healing as such, but let's give some ideas here. So one of the sort of motivation of this kind of work, and let's say I was one of the first to formalize this notion, and it's like in my PhD. But the idea was we had a lot of epic failures happening. They still happen, but this is an old slide. So some point Skype failed in 2007, and Facebook and Twitter, and they keep failing. And some of it was due to their what we call as self-healing algorithms. Now here, let's sort of see how you deal with failures. So there may be two different ways to deal with failure. The first may be how the first, which is the second in the slide, is a computer network. An old kind. If a component fails, you just open the computer, you replace the component, and you restart the computer. Right? That's sort of the older way. Or the brain. Now the brain cannot stop, right? So it cannot really stop and rewire and continue. If it does, then we are gone, right? If our brain stops, we are gone. But the brain does have failures happening all the time. So the brain does lose cells, the brain does lose connections, but it fixes them, continues. So the idea of self-healing is to be like that, to be able to fix and go on. Now this is not just an ideal thought. There was a lot of heavy research going on for many years. Partly there's the IBM's Autonomic Computing Initiative, which is nature and bio-inspired, and they came up with these 4 properties they call self-chop. For example, self-configuring, self-healing, self-optimizing, self-protecting. And the idea is, if you have many of these properties, you can go towards what are known as autonomic systems. So all of these self-managing systems need these properties where they can handle things by themselves. Now here the important thing is self, right? So when I was doing the healing game before, when I showed you the healing game before, we were an outside entity changing the graph. But if in a self-star system, the components of the system themselves have to do the things. So they have to work without an external entity to change things. So that becomes challenging. So a self-managing system, for example, could be like a very clever robot, a very fully autonomous system kind of thing. So it could be self-configuring. It can change its configuration for its needs. It can be self-healing. That is, it can recover from attacks. That's why self-healing, self-optimizing, trying to do better for what's need to be done, or self-protecting, being able to protect itself in advance of attacks, right? So now going towards a high-level definition of self-healing. So we can say that a self-healing system is a system which is at the moment it's in a correct state. It's working fine. Then there's an attack from an adversary, from somewhere outside who wants to damage you, and then it only goes only temporarily out of a correct state. So even though it's been attacked, it's going to continue. For a little while, it'll be in trouble, but then it comes back. Right? It's like us when we get sick, we sort of recover and come back. Till unfortunately one day, if we do not recover, then we do not recover. But usually we recover and come back and are fit and go on, right? So now here the idea is that you're going to be able to maintain certain properties. So we are when we are going to design self-healing systems, we are going to say, these are the properties I want to in my state, and these are the properties I want to be maintained for my state to be good. And then, you keep maintaining them, but at the same time, you do not expect everything to be just the same as before. You may not come back to exactly the same shape, but you'll probably come back to what your acceptable shape, right? That's the idea. Okay. Right. So if we sort of look at a few bigger self-healing themes, so the main theme which I'm going to deal with mostly today is, designing these resilient distributed architectures, or what we can say is P2P, topology maintenance. There is something which I will formalize, but for example, peer-to-peer is a good example in that sense that even to self-heal, you need certain certain help from the network. You can't just change things. So, for example, when we played the games, we were able to add back edges. So we need that kind of facility, and peer-to-peer, for example, is suitable for that kind of thing. Then you could, if you sort of constrain the memory on these, for example, look at compact routing over, again, these networks, and this is quite pertaining to, for example, Internet of Things. You could now, restrict some things. And there are other themes which have not been explored well at the moment. So there's a lot of opportunity here, for example, in many kind of actual networks, software-defined networks, or social resilience. For example, what's happening if you have terror attacks, things like that. Can you define self-healing in those sense and try to use our ideas on those, right? So those are some things to try for. Now, what we will do is we will restrict ourselves to a very simple setting. Like I said, a very sort of simple model which is going to heal for one kind of attack, and that attack is node failures. So we're going to talk about node failures and also actually insertion at some point. And now we want to be able to handle nodes going down. So what can we do? One simple idea, which is of course used practically many places, many times, is to just add some redundancy. So that means you have a node and you have a backup of that node. For example, you have any component, you have edges, you have a backup of that edge, whatever you like. You have some information, you have backup of that information. So you basically add redundancy into the system. So when one thing goes down, you can bring back the backup, right? So that's one idea. For example, if you're worried about connectivity, you can use a k-connected graph. Now, this means that you can lose up to k-1 vertices. You will still be connected if that's what you're looking for. So, but your degree now must be at least k for every vertex. Now, this can be expensive, right? So maybe we want to do something else. So in self-healing, we try not to build redundancy. We try to do what we call as responsive. So we don't keep backups, but we try to do changes on the fly, right? And the first thing you think about when designing this algorithm is, like I said, the adversary. And adversary is a very useful idea, of course. So it's just a theoretical abstraction which covers everything. It covers opponents, environment, internal faults, limitations, anything you can think as adversary. Now, of course, if you have success against stronger adversary, the stronger are your guarantees of your algorithm, right? So the stronger the bad guy, the better your algorithm is. And this is one way we think about faulty systems, dynamic systems, etc. Right? Okay. So let's sort of now define the self-healing model as a game in a little bit more formal manner. So what do we have? We have a distributed network, which is the graph, let's say, G. You have an attack action. So what is an attack action? It's like an adversary which comes. Now it's either inserts a node or deletes a node. And we're going to do this only one per round. It comes, attack, deletes one node, inserts one node in every round. And then the algorithm gets to do the healing action, right? Now the healing here is interesting because, like the game we played before, that could be called as a centralized kind of a healing where you know the whole system and you decide. I think it's even then it's not completely trivial what edges you would add if you have certain cost associated with it. But here it's even more the self-healing in this setting, because after every adverse reaction, what you're going to do is we can add or drop edges between pairs of nearby nodes. And in a distributed system, it basically means the nodes themselves decide which edges to add or drop. So they have to make this decision locally, and this will heal the network, right? And as sort of Armando pointed out in those examples, probably intuitively what we start thinking is, how do we stay connected? Because now the adversary can easily remove a cut vertex, for example, and disconnect your network. But the thing is, how do you know if the network is broken into 2 pieces, or it's broken into 5 pieces, or 25 pieces, or not broken at all, right? So we could look at the graph and know, but if these nodes are only able to see around them, can they know that this has happened? What will they do? So that's sort of a question to think about, right? So something to think about, but that's the model, right? So basically, this is the what's happening. You start with a distributed network. Now, distributed, as I said, means that every node only knows it locally. So let's assume every node knows only about itself, and it can send a message to its neighbor. It knows its neighbors. So that's all it knows, only the local neighborhood. And then you keep continuing this forever. So there's always attack, there is healing, attack, healing, goes on forever. That's sort of the idea. And you can maintain, then basically you try to maintain some property, right? So this is, previously, a lot of studies were done on networks where edges were disappearing and coming back. But this sort of resilience concept is about nodes going away or coming back. Any questions here? Let me know if people have any question or need a break.
I do have a question.
Please.
It sounds a bit weird, but anyway, I will try.
Yeah, please ask. I can hear you.
Yeah, so here the healing is involves just dropping, and adding edges. But does it make sense to consider that maybe, that I don't know, the algorithm decides that a node should kind of disappear so that some things, I don't know, that's better for a specific target, or that doesn't make sense?
That's an interesting question. So if the algorithm decides to drop a node themselves, is what you're saying?
Yeah.
That's interesting. I didn't think on that sense, but of course it's not very useful for it to be able to insert a new node, I think, because it can just replace the node which has gone by a new node. If it drops a node, that's interesting. I haven't thought about that. So it's an attack which the adversary does usually in our model. So it'll be interesting to think, why do you want to drop a node? Maybe you save something. I think it's possible. Maybe if you want to save on, let's say, the degree of existing vertices or nodes, you may. We didn't consider that, but maybe it's a possible attack action, but not completely obvious.
Yeah, maybe it's not helpful at all. So it was just a question.
I mean, you may have to find a scenario where it's useful to drop nodes. I mean, I can possibly think that, if a neighbor of a node gets very overloaded, and you can spare this node, you may want it to drop out. I mean, I think it's possible that it's useful, but we haven't thought in that manner. Yeah. Any other question? All right, then I'll move on. Okay, so let's look at this by examples. So let's look at this illustration. You have so this is similar to the game we were playing before, but now I'll play out the game a little more fully. So you have a vertex V, and the adversary decides to delete this neighbor of V, and this neighbor of V is now gone. And as you can see, the network split into 3 pieces, 3 connected components. So obviously, it seems we should be wanting to get them back. So we sort of connect all of them up. Now, if you think about it, if we were doing as we did before, like at that point, I think Armando pointed out, we add 3 edges, right? But now, in fact, we've added 5 edges. So why do you think we have done that? Why did we add back 5 edges instead of just the 3 edges? Any intuition? So the thing is, we possibly cannot add back less edges than this. Why? Because like I said, you know, the edges are being added back by these nodes themselves. And unlike us, they cannot see the graph. So they can only see their local. So they are informed that their neighbor has gone, and they only have some local knowledge. Now, okay, they have some local knowledge, which is more than I've told you. So, but they have some, let's say they know neighbor of neighbor. So they have no idea of knowing whether the graph has been completely split or not split at all. So they have to just connect everybody up, right? So they cannot really take the risk of, otherwise they may have to find if they are in a connected component, but that can be quite expensive. So they basically, all of the yellow vertices basically connect themselves up in some topology. Okay, at the moment they just connect themselves up, right? Now, let's say another vertex node is attacked, and this is what happens. Now, actually here you see, if this was a centralized algorithm, possibly you would have done nothing if you were happy with things like distances, because it's still a connected component. But like I said, these nodes have no idea of knowing if they're in the same component. So they still add back some edges. Okay. Now, the question is this sort of a naive approach? And then we go on here. Now this is deleted. Now you still have a few nodes, right? Now again, how do we connect them up? So do we just take all of the neighbors and just connect them up? Do we connect them up randomly? Do we connect them up as a line? What do we do? So we connect them up in some manner, right? And so on, this goes on. So this is basically the self-healing game. And now hopefully you're beginning to appreciate that every way to connect up may not be the same, may not give you the same results. So you may have to do some thinking there, right? Okay. So I will tell you some of the problems in what we did right now. So if you look at the left side, the graph G0 is the starting graph or the starting network. And on the right side, the graph G3 is the graph after the 3 deletions have happened. The edges in the orange are the edges we have added back, or the nodes have added back the self-healing edges. You can see that the degree of V initially was 2. Was just 2, right? The degree of this vertex V was just 2, right? And now it has blown up to 5, right? Sorry, where's my mouse? Okay, so now it has blown up to 5, right? So what you can see is that the node gained 1 degree for every attack, right? Even though the number of vertices are coming down, actually, right? So you can see, even though the number of vertices are coming down, it's gaining degree, and it's like 1 per attack, right? So that doesn't seem great. So okay, that's one problem, right? So okay, how do we sort of tackle this problem? So one way we could tackle this problem is by connecting up the vertices as a line, right? So we just make sure that we connect them up as a line every time there's a deletion. And why as a line? Because the line has the least degree increase. So that's the best we can do, and we should not get any degree increase possibly if we just connect the neighbors as a line. If, for example, V is at the corner, so this may work. So we may connecting up as a line, but this will ensure you get low degree increase. But the problem is now the diameter of the distances can blow up. Right? Imagine things start getting connected as a line, so that may be a problem. So instead of that, we could go reverse. We could go as a star. or as a complete graph. So now you could have take one vertex as a center and connect all the neighbors to that one, and then you got really low distances. But now the problem is the degree really blows up. So now V's degree can be even higher than we had before. So you have a couple of challenges. Firstly, a low degree increase could mean a higher diameter stretch for expansion, or a low diameter could do the other way. So it's a high degree increase. So you have these properties which are conflicting with each other, right? So now if you want to balance, for example, just these two properties, or plus connectivity, let's say, then you have a challenge, right? The other challenge is what we already sort of discussed, the local fixing of global properties. So these are sort of global properties, distances, etc. But you just have local ways to fix them. So how do you do that? And this basically is because of limited global information and limited resources and time constraint. And this is basically the challenge of distributed computing itself, right, to handle all of these things. All right, so these are some of the problems we have. So we have to then come up with ways to balance them. Now, for example, here we have a series of graphs from an algorithm Dash, which in IPDPS 2008, where you've cycled through, let's say, initially you had 100 nodes, and now you sort of follow that particular algorithm, which I'll talk about a little bit later. And the red edges are the ones added by the algorithm, self-healing algorithm, and the gray ones are original ones. And as you can see, we are able to maintain the graph, and we are not losing shape completely. And what you can just see by an eyeball is at least you are always having connectivity, right? You're always maintaining connectivity, you're still able to go on, etc. So sort of gives you a rough idea of how these algorithms can work. So of course, adversary keeps deleting. At some point it'll delete all the nodes. I mean, that's not our concern. Our concern is just to be able to maintain the shape as these deletions happen. All right. So what are we typically looking for in self-healing algorithms? So we basically define some goals. And in this case, most of what I'm presenting is going to talk about topology of the graph, or topology in the graph. So we're talking about set topological goals. So the self-healing goals are, firstly, it should be fast, the healing. We want to fix things very quickly. And certain properties should be maintained within bounds. For example, connectivity, degree, since degree is amount of connections the node needs to maintain, the diameter of the stretch, which corresponds to basically latency and how much communication is needed, expansion or spectral properties. Now we increased the number of things we started maintaining, and we, for example, even included spectral properties and expansion, etc. And then whatever you want, right? Whatever you think is your requirement, you may want to add it here. Right? These are the typical ones, or ones which we have managed, but there's no reason for you not to be able to define your own property which you are looking for and trying to maintain. It can be completely different set than ours, right? So, and finally, what you also need to define some cost metrics, right? It's not free, so you have to is your algorithm good or not? Now, typically in a distributed algorithm, you have time, like the distributed time. Remember that clock tick I was talking about, that every time the clock is ticking. Now, how many clock ticks do you need before you fix the network? That's your cost. And the number of messages you are going to exchange over time. And also, you may want to think how much you have lost in terms of your properties, right? So they are still in the same ballpark. It's fault tolerance, but maybe have you lost a lot? Have you lost a little bit? How much you're able to give, right? So these are kind of things you may be looking at, right? Now, if I was to now define this in a broad sense, this is what we need to understand. So if you talk about a self-healing system, now imagine, you don't even need to imagine network graphs, whatever you like. You can just think of this. I want to talk about a self-healing system. So now the system, what does the system need to be? The system needs to have two properties. It needs to be responsive, and it needs to be reconfigurable. So responsive basically means when an adversary attacks, it should be able to respond. That is, it should be able to detect, for example, that it's been attacked. So fault detection, or whatever you think. I mean, in fact, in our algorithm, we are assuming that somebody tells us that fault has happened, and it needs to be reconfigurable. Now, reconfigurable is basically what we said as adding edges. So now this need not be edges; it can be whatever you like, but it needs to be reconfigurable. That is, it needs to be able to do something, change something, right? Now there's going to be an attack action, and the attack action is basically this adversary. It comes, it attacks. Now in our case, the attack action is deleting nodes. In your case, it could be whatever you like, right? And a healing action. So after the adversary attacks, you have to repair locally and quickly. Now again, this healing action is something you can define, whatever is in your system, the right one, but it needs to basically be responsive, and it needs to be quick, happen quickly, and fix things quickly, right? So that's basically, at high level, if you were to design, we had to think about this, right? Any questions here? So this is sort of my high level notion of what a system should look like, and now I can sort of go in a bit more detail. And well, to continue, like I said, healing should be fast. So, and this is about fault tolerance. So you're not looking to get back exactly the same properties. You're just looking to maintain them within certain bounds. Just list the properties you want, right? So now you put out the invariants you need to be bounded, and you define the costs you need. The cost could be per healing, per round, per attack, or it could be over time, over all the attacks which have happened, or what are your costs, right? Both are fine, both are needed. Now, some of the self-healing algorithms we have had, some of the proposals we've had are, for example, this. I mean, not just mine, but other people also. So, sort of one very preliminary work was done by Bowman et al. In SSS06, and then a number of algorithms followed. A lot of them are ours, and so on. We'll look at some of this now. So our self-healing algorithms, in which I have been involved in, basically look a bit like this. So you sort of begin with this idea of this algorithm called dash. Now I have separated this into non-virtual and virtual. I'll tell what these are. But let's say we sort of begin with this algorithm dash, and it only tried to maintain connectivity and degree increase. It didn't bother about any other properties, and even then it was non-trivial. And then we thought, okay, let's bring on something else. So we, I had modified this slide, but seem to have lost the diameter here. So we added diameter. So we said, okay, we'll maintain the distances, we'll maintain the diameter of the network, and that gave us forgiving tree. Then we said we'll make it even stronger. We'll not just diameter, we'll do per node stretch. Plus we also allowed insertion. Both of these are deletion only. And we get forgiving graph. Then we started adding, we said not only distances, we'll also maintain expansion. So now you can think, for example, we came to Xseal here. We are maintaining connectivity, we are maintaining degree increase, we are maintaining distances, and we are also maintaining expansion. Of course, these properties are related to each other in some ways. And then we even maintain density in the Xseal plus and so on. And there is another notion which was very interesting, and which I worked with actually Armando here, is that we thought about even when the graph is changing, when we're doing self-healing, what happens to the processes which are on this network, So the network is not existing just like this, just like a topology. Some things are happening. And one of the things which could be happening is routing or compact routing, which is basically managing to do routing with low memory. So we said, okay, what if routing is happening? Can we still maintain routing while the self-healing is happening? So that is something I call functional self-healing. And in this we have a couple of works. Of course, if you look at this picture, there's a lot of many things which can still be done, right? So that's sort of the idea. And now the first question here, and maybe this will take us to the break, or we'll do a little bit further, is why would you even want to do this P2P self-healing, right? So now I'm going to concentrate on just this peer-to-peer idea. Now peer-to-peer, if you know a bit about this, is you can imagine that you have is what you have on the internet, for example, or other things. Overlay networks is what I'm sort of thinking about. So overlay networks means you actually have a real grid, real infrastructure below. You can connect to anybody you like, but you don't connect to anybody you like. You only connect to a few people. For example, again, on your friend network, Facebook, WhatsApp, whatever. These are overlay networks, peer-to-peer networks, whatever you want to call them. That you make connections to a few people, but you can make connection to anybody you like. But if you connect to everybody, it's expensive, whatever, right? So everybody is connected to a few of them. But if you want to connect to somebody else, you can, if you know their identity. If you know the IP address of another computer, if you know the name of a friend of a friend of a friend or something, you can make a connection, right? You can send a friend request, right, and get a new friend. So that kind of network is what we're saying. So now you see you have a responsive, you are allowed to respond. You are allowed to request a new friend, for example. So this is a sort of a self-healing idea again. So firstly, why would you want to do this in regular networks? So let me give you an intuition. So what you can do here is something very interesting. So the question here is not really why, the question is more interesting in some sense. Like, if you want to engineer a very good network, what can you do? And then you can involve self-healing in this, and then you maintain a very good network, right? So the idea here is you can start from any bad topology, and if you get to a good topology soon, for example, an expander network is a good topology. If you don't know what is expansion, I mean, just think of it as a graph or a network where everybody can reach everybody else, through very short paths, even without having high degree. So that's kind of very good network. And then you can get to this really good network, and then you can just maintain it using self-healing. So the advantage of self-healing is once you have a good thing, under attack, you can still keep maintaining it, right? So here, let's go to another model again, slightly more formal model, which is again going to relate to our work. But also I want to motivate here, how can you reach a good network from any network, any bad network, very quickly. So this is sort of our work from last year called Deconstructor. I'll talk about this. And in this we introduce a formal model, from a slightly more formal model, which we call as P2P congest. So now, and this is related to self-healing, to a self-healing thing. I'll explain how they differ slightly. So P2P congest is a congest model extended to peer-to-peer or overlay networks. Now, what is the congest model? Like I sort of said a little bit, what we are saying is we are restricting the size of the messages. So this is the practical model. So this is like saying, if I have to send a message to somebody, I can only send this message of this size, which is reality. You can't send everything. So for example, if you can send everything, which is known as a local model, then every problem can be solved in the size of the diameter of the network or the graph. Why is that? Because in diameter time, so in the first round, I send all my information, which is all I know about all my neighbors, right? Then I send it to all my neighbors. In the second round, I know all the information from my neighbors about all of their neighbors. So I know everything I need to know 2 hops away, right? Then I get to know everything I need to know 3 hops away. Similarly, in diameter time, I don't know the whole network. And in distributed computing, I didn't mention it, mostly we assume that the local computation is free, which means once you know the whole network, you can solve any problem you like, any NP hard problem, whatever, right? So we are not going there. So congest means you practically send small size messages, and which is the practical model. And now you're talking about this in peer-to-peer networks, which means basically you have the changing graphs. So let's say you have the graph G1, G2, so on, where G1 is the initial network, and initially nodes only know their neighbors in G1. Assume for now this is synchronous and congest. So each round nodes are going to do what we said before. They can send, receive messages of size log n. But now what you can see is they can also send the identity of each other. So AB, for example, U knows its neighborhood ABC, and it can just send it can send tell about a couple of his neighbors to its neighbors. And now C basically knows about U. In the next one, it can send U's identity to D. And now C knows about U, D, E is its neighbor. To U, it sends the identity D. To C, it sends the identity U, and so on. But also the same round. So let's look at the steps. So first step, nodes can send and receive just like in regular synchronous congest. But in the second step, they can also reconfigure. So in the second step, basically is what we were saying, you can change edges. So in the second step, you can ask for edges to be changed like we have in the self-healing model. The only difference here is there is no attack happening, but the nodes are asking for edges to be changed every round. So the big difference is in regular self-healing, when an attack happens, you can do changes. So every round is driven by an attack basically. But here you have you can think as changing every round. Now, right. So like I said, in a self-healing distributed model, it's just like the P2P congest model, except that every round is initiated by an attack, which is like removing a node. And the other difference is actually we don't assume synchronicity. The repair can be asynchronous. Nodes can just, the order of repair is not dependent on time. This hopefully will be more clear, but it has to finish before the next attack. Okay, so this is sort of the idea here. And so here we sort of go into the well-known field of P2P construction and maintenance. So there's many algorithms known which for many different ways you can fix things and all of that. And for example, our deconstructor. Why do you need such algorithms? Like I said again, because in the world of overlay or peer-to-peer networks, you have a collection of say changing servers, and you have an underlying network which is fine. You just choose a good subset of edges, and you want to construct this kind of a new, subset which has say low degree, low diameter, good expansion, etc. Whatever you like. And as motivation, for example, Bitcoin is a peer-to-peer overlay network, and where you are using this overlay for communication. You need it to be reliable, you need it to be maintained, and all of those things, right? And you need to run it despite failures. So here our paper deconstructor basically gave us one possibility. I will go over this very quickly. So it's a practical it's an algorithm which will reconfigure any bad topology or whatever topology you have to a good topology within logarithmic rounds. So quite fast in small messages. I will not go into too much detail, but you achieve most good topologies which are small diameter, low degree, which can be done quite fast. It is self-repairing, dynamic, etc. with low messages and low overheads, right? Okay, I will go through this quickly. I will mostly skip this, but basically it tells us we can do it quickly. All right, so back to self-healing, and I think we'll do a little bit of start before we go for a break. I think most must be tired by now. All right, so mainly I will talk a bit about Dash, forgiving tree, and forgiving graph. And that should be good enough. So first, let's look at this short history of how we tried to get to self-healing. So like I said, the first idea was given by this paper by Bowman and others, which was quite, the idea was straightforward. They said, take a node, a deleted node, just connect its neighbors in a line, and what do you get? So of course you'll still get connectivity, but you may lose a few things. Now we know a lot more about what you lose. That's how sort of this kind of idea started. And then we sort of came up with Dash. Now Dash is degree assisted self-healing. Now here the idea was again sort of simple but useful. So we said, okay, we can do better than connecting them by a line. Why don't we try something a little bit smarter? So what we did here was you connect the neighbors of the deleted node again, but you keep track of the history in some ways. So so now you connect them up as a line. So instead of as a line, you connect up nodes as a tree. But what you do is you keep track of your degree increase. So that's why it's degree assisted self-healing. So if in the past your degree has increased by +2, and let us say +2 is quite high, and your other neighbors have not increased their degree, what do you think is a good position for you to be in? So what do you think in a topology? Now let's say I want to connect them up as a tree. Where do you think I should come in the tree? Let's say I have the highest previous degree increase and I am going to be connected in a binary tree. Where do you think I should be connected? Any intuition? If I haven't put everybody to sleep by now. So I am going to be a node in a binary tree. Where do I have the least degree increase? Or in other words, where do I have the least degree in a tree? And the clue is a lot of nodes have low degree. Sorry?
At the leaf, no?
Exactly. So at a leaf. So if we are a binary tree, for example, almost half of the vertices are going to be leaves, right? So the idea here was quite straightforward. So it's an intuitive idea. If your previous history is that you have increased your degree already a lot, you will now be given preference and you will become a leaf in the new change. And if you haven't suffered degree increase before, then you go in the middle. You go in the center, your degree may go up by, your degree may be 3 now, right? If you're a binary tree, your degree may be at most 3, so you may increase by +2. So that's sort of simple idea. Now, since half of the nodes can always be spared a degree increase, now you can look at this over period and you can analyze this over time, and then we sort of get the idea that you can maintain degree increase by at most, you can limit it to at most 2 log n if you just use this idea called degree assisted self-healing. There's no guarantees on diameter, but we were able to conduct a number of experiments here on different attack strategies, and and many different healing strategies. And now if you look at this graph, here you have maximum degree increase, and here you have this is actually in 2 to the power, so the log n is base, I forget now, base 10 or base 2. So you can see that how the dash and this S dash are able to keep the degree increase very low, whereas other kind of healings where you were just connecting up in other ways, some of them really shoot out, above the thing very quickly, right? Sort of the idea here. And then we also looked at stretch. Now stretch, basically, we'll revisit again, is this degree increase over pair of nodes, and we saw that some of the other strategies were doing better with distances, and our strategies were able to do over time good, but at some point it just went out of control. So just sort of this green line keeps going up and up, and just sort of starts going bad, but it sort of still maintains it sort of over time, keep going, right? So that's sort of the idea. Now here a question which we have sort of already answered, that if you are the bad guy, who would you attack? What would be a good attack strategy for you? And during all of these simulations kind of things, we sort of realized that possibly the nicer idea was not attacking the node who you want to damage, not deleting the node who you want to damage, but instead attacking its neighbors. Why? Because the degree increase, if you attack a node's neighbors all the time, you'll start offloading the degree of that node to this node, right? This will have to take the neighbors of that deleted node all the time till ultimately its degree becomes too much, and then it can collapse by itself, right? You don't have to attack it directly. And for example, this one of the intuitions we got from it. All right. So after this, I'm ready to discuss forgiving tree. Is this a good time to take a break then?
Yeah.
So yeah, I think it's probably a natural time. So what do? We take a half an hour break?
Yeah, it's scheduled half an hour, I think so. Yeah, let me see.
Like 5 past 6.
Yeah, it is planned here to resume in yes, 3:30, which would be.
Well, I can go on for a few more minutes if you think it's sort of early to take a break.
As you wish, as you wish.
Okay, maybe we'll progress a little bit on this and then we take a break at in 5 minutes, and then we get 35 minutes break. Right. So okay, now I'm sort of we're ready to discuss some of the more interesting algorithms here. So forgiving tree was a paper we had in POTC 2008, and now that you have some idea of dash, you can sort of move to forgiving tree. Again, here what's going to happen is you have the network or the graph, and nodes are going to fail in some unknown order, which is decided by the adversary. The adversary decides how to fail them. You have the P2P congest kind of model, which I just talked about. So after each node deletion, we can add or drop some edges between pairs of nearby nodes to heal the network. And the main result we get is that we are now able to maintain not only the degree, and the degree we are able to maintain surprisingly really well just by +3. So it doesn't matter how many attacks happen, how many deletions happen, a node's degree goes up by at most +3, not more than that. And the diameter is also really bound, and diameter is bound to within log D. So log D here is the maximum degree, or delta is often called. So you maintain the diameter of the whole network, whole graph, just to within log delta, not more than log delta, and degree increase just +3. And moreover, the repair is very quick. So repair happens in what we say constant time, that is almost immediately, and it involves only at the most max delta or maximum degree number of nodes. So it's quite fast, efficient algorithm, and as you can see, we're actually maintaining these two properties which are like opposite of each other. And moreover, it has a matching lower bound. So in fact, you cannot maintain distance and degrees in a better factor than what we did in this work. As motivations, we tried to maintain trees, and trees are in some sense the worst ones for maintaining connectivity, because as soon as you lose a node, you lose connectivity. But a new innovation we did here was we went to the virtual space. So we started maintaining what I'll explain soon, like a virtual tree. It's not the real network we have, but a virtual network on top of the network. And in this way, we were able to maintain the tree, the topology, and sort of keep track of, remember the idea from Dash that we wanted to keep track of which nodes had increased their degree already and keep them on the leaves. So in somehow were still able to do something like that, but even in a nicer way, and also not blow up the distances. So what is the first thing we do? So the first thing you do for forgiving tree is you have, you're given the graph, and you're going to maintain that graph, right? So you're not given a tree, you're given an actual graph. You want to maintain that. First thing you do is find the spanning tree. So you keep a spanning tree. You make it a rooted spanning tree. So it's a rooted spanning tree. And now you're just going to maintain this tree by always inserting a balanced binary tree. So similar, in some sense, similar idea from high level to Dash, except we are not doing all. We're doing a different way. And so the main thing you do is each time you have a vertex, you replace it by is deleted, you replace it by a balanced binary tree. And also at some point you may have extra nodes which you don't need. You remove those nodes, which is sort of technical thing. And then somehow the surviving nodes are going to simulate the virtual nodes. If you look diagrammatically, which is much more easy to understand, I suppose, this is basically what's happening. So there are only two main actions which you do. So firstly, you replace this vertex V by a balanced binary tree of virtual nodes. So this I'll sort of explain. So these virtual nodes are not existing, but we create them in memory, in nodes memories. And the other thing is, so maybe look at them one by one. Okay, let's look at this. So node V is gone. You're left with P, A, B, C, D, E, F, G, H. Now you put this circle here. So A, B, C, D, E, F, G, H, you can see are still on the leaves, but you put in these round circles what we call as virtual nodes. So these are not really there, but we have created them. You can see they have the same labels as the leaves. So there is a round node called A, there's a round node called B, round node called C, all of these are there. In fact, they are exactly the same here as A, B, C, D, E, F, G, H also. But as you can see, it's a balanced binary tree. So when you have 8 leaves, you have 7 virtual round vertices here. But we also add another square one. The H is also a virtual one. So we added another one here for technical reasons. Maybe we'll get to that. And you connect that up to P, which is already here. P doesn't have anything here because now think of this as a directed tree. So P is the parent of V, and these were V's children. So V's children have created a virtual node each, and now it's also connected as a tree, except that these don't really exist, but only in virtual memory, and connected up. The second operation you need to do is that at some point, if you have leaves, for example, when the deletion happens at the leaf level, then it has no child, right? So then you can't really create, you can't really bring in more nodes because it has no child. So instead, what you have to do is remove these extra virtual nodes. So for example, Z here was simulating this Z up there. So you have to do a short circuiting. So you short circuit somehow this virtual Z is removed, and this virtual Y is now taking the place of Z. So this sort of some technical tricks you do here. So these are the two operations you do. If you can do those, you get the forgiving tree. And there are some advantages to this virtual approach, which we'll discuss after the break. And then we'll see forgiving tree reaction, and then we'll move to forgiving graph, so on, right? So I think this is a good point for a break, and we'll see you in half an hour, right?
Yeah. Okay.
Thank you so much.
Is the streaming stopped now? How does it work? Or
I will stop it. I will stop the stream and we restart it after the break, okay?
okay.